Hi, this is the video that contains the solution for 2014 Mechanics number 3. So let's see what we got here. This looks like fun. Here's a top view of this person standing on the edge of this circular platform. I guess that's the little ball that they're holding. So let's see what's going on here. Large circular disk of mass m and radius r is initially stationary on a horizontal icy surface. Person of mass m over 2 stands on the edge of the disk. Makes me think, right, moment of inertia kind of thing. This is a disk, it's a circular disk, so that I have a 1/2 mr squared, and then the person would have you'd have to add their mass and mr squared for them. Their mass is m over 2, so anyway, sorry, getting ahead of. Without slipping on the disk, the person throws a large stone of mass m over 20 horizontally, so it's along a line that contains the center, so there would be no torque there, right? It wouldn't spin, it would just push back. With a speed of v sub 0 from a height h above the ice in a radial direction as shown in the figure above. So radial direction just means along a radius. Coefficient of friction between the disk and the ice is mu. All velocities are measured relative to the ground. The time it takes to throw the stone is negligible. Express all algebraic answers in terms of all that stuff and fundamental constants as appropriate. All right. Derive an expression for the length of time it will take the stone to strike the ice. That is just a horizontally launched projectile. So it will take the same amount of time for this to hit as it would take if the person just dropped it, right? Because the initial velocity in the vertical direction is 0. So I have an initial velocity of 0. My acceleration is negative g, negative 9.8 meters per second. The distance, my displacement, is negative h. You could have made those both positive if you took down to be the positive direction. That's fine. And I want to know the time. So that leads me to the displacement is equal to 1/2 at squared plus vit. That's one of the equations that is on your formula sheet. So that displacement is negative y is equal to negative g over 2 times t squared, and then this term is 0 because that's 0. So t would be equal to the square root of 2h over g. Right? Part B. Assuming that the disk is free to slide on the ice, derive an expression for the speed of the disk and the person on it immediately after the stone is thrown. So this is a momentum problem, right? I have initial momentum, and it's not rotating, so this is just regular momentum, not angular, not yet. So my initial momentum is equal to my final momentum. The initial momentum is 0. Both person and disk and stone, they're all at rest. And then after, the person, the mass of the person plus the mass of the disk times their velocity that would be their momentum, and then the rock or the stone, mass of the stone times the velocity of the stone. All right, so let's fill in the stuff that we know. The mass of the person is m over 2 and the disk is m, so that's 3/2 m times the velocity, I guess that's what we're trying to find, right? Plus the mass of the stone, so m over 20, times the velocity of the stone is v sub 0. You got that set up the right way. So solving for v, these will cancel out, and I will get, let's see if I can do this, I get negative maybe I should write it out. I'm going to write out one more step so I don't mess it up. Good advice, right? So that's 3 halves v is equal to v sub 0 over 20. There's a negative here. We're going to end up losing the negative sign in the end because they're asking for the speed, not the velocity, right? But it makes sense to be going the opposite direction. So I'll multiply both sides by 2/3 and get that the velocity would be v sub 0 over 30, so the speed is equal to v sub 0 over 30. Okay, so that's just a momentum problem. Derive an expression for the time it will take for the disk to stop sliding. Well, the time that it would take, if we're talking about time, I think we've got to be talking about kinematics, right? That's how we get to time. Or, actually, I'll show you 2 ways you could do this. One of them would use kinematics. So if you use kinematics, we know that there's an acceleration because of the friction, right? So the frictional force would be equal to mu times the mass of the disk with the person also on top. So that'd be mg. That would be the frictional force. Right? You can't forget the person standing on top of the disk. And that's the only force acting on the disk, right? So that's equal to mass times acceleration. We would notice here that this is a negative frictional force. It's the opposite of the direction of motion. So I'm going to make that negative, so I get a negative acceleration. So A, the m's would cancel out. The acceleration is negative 3 halves mu g. So that's my acceleration. The initial velocity, sorry, I don't want to call it v sub 0, that's something else. The initial velocity is what we just found. That's v sub 0 over 30. The final velocity, we want to know about it coming to rest. That's 0, and we're trying to find time. So that leads me to the equation Vf equals At plus Vi. So Vf is equal to A t that we're trying to solve for, plus Vi. So let's see, t will be equal to, here I go again. We're skipping a step I probably shouldn't skip. 2/3 2 over 30. So I think, I'm going to take my chances here, that it's going to be v sub 0 over 45 mu g. You can check my algebra there, and you should not skip steps like that. What a bad example I'm setting for you, but I'm pretty sure that that is right. That's just from adding this to that side and then dividing by 2/3 mu g. I think that that's right. All right. That's the first page of that. Now, the person now stands on a similar disk of mass m and radius r that has a fixed pole through its center. So it's now an object rotating on a fixed axis. It only rotates on the ice. The person throws the same stone horizontally in a tangential direction at an initial speed v sub 0, so same speed. And the rotational inertia of the disk is mr squared over 2. And we want to derive an expression for the angular speed omega of the disk immediately after the stone is thrown. All right. So this is another momentum problem, but this is conservation of angular momentum. So we have the angular momentum of the stone, which is like a particle, is going to be equal to the angular momentum of the disk plus the person afterwards, right? So for the stone, that is R M V. It's thrown tangentially to the disk, so I don't need the sine theta part, equals, this is I omega. So the I is the 1/2 m r squared of the disk plus the mr squared for the person. Person's like a particle, and their mass is m over 2, and they're standing at the edge, r squared. That's the person, times omega. All right, let's see what we can do with that. So I've got one of the r's will cancel out everywhere, so, and one of the m's will cancel out. This is the same m, right? That's the capital M. So here I think I have v sub 0 over 20 is equal to 1/2 r plus 1/2 r, that's r, times omega. So that's simplified a lot. So omega is equal to v sub 0 over 20 r. All right. Oh, do I have another page? Nope, that's it for that. And part E, the person now stands on the disk at rest, r over 2, so that would be like here, from the center of the disk. And the person now throws the stone horizontally with the same speed in the same direction. Is the angular speed of the disk immediately after throwing the stone from this new position greater than, less than, or equal to the angular speed found in part D? Well, we could just figure that out. How would that change this? So I would still have the r, the stone's momentum now would be r over 2 times m over 20 v sub 0. And it's not totally, if you're just thinking, oh, well, you know, that's smaller, so obviously this would be smaller. I think it's not totally, excuse me, obvious, because this is also going to change, right? So the disk still has 1/2 mr squared, but the person is now further in, so their I is smaller. They're still m over 2 mass, but they're now at r over 2, so when we add them as a particle, that's where they are. So I think, I don't know, I think I'm just going to crunch the numbers here and see what it comes out to be, and we'll compare. I don't really see a better way of doing it than that. So here, an r and an m will cancel everywhere, so this would be v sub 0 over 40 is equal to, and now I have here 1/2 plus 1/8 of an r, so that's 5/8 of an r. So omega is going to be equal to v sub 0 over 25r. It looks like, if you simplify that, right? 8 over 40 gives you 1/5, and then that 5 moves to the bottom. So this is less than. Less has two S's. Less than. So it did go down, but my guess is that if you just said, hey, look, this is going down, so that goes down, I think that it's not a direct proportionality, because this also changes. I think that that probably would not get you full points. It would probably get you the point for having the right thing checked. All right, 15 minutes. Time's up.